Hello and welcome to the first episode of the Insulin360 podcast, the podcast that takes a deep dive into metabolic health. I'm your host Joe, and in this first episode I want to set the scene a little bit. So I'll briefly talk about why I started the podcast and what I've got planned for it. Then I'll move on to talking about the history of insulin. So from 100 years ago and the discovery of insulin and its first use in human patients, up till the modern day and kind of looking at this exponential growth in our knowledge and understanding around this area. And also looking further back in time to some of the ancient medical traditions like traditional Chinese medicine or Ayurveda and seeing what they have to say about insulin issues. Then I'll move on to some of the basic physiology around insulin, where it's produced, how it's regulated, its various different effects on different tissues, so that we have a good foundation moving forward. So if you like the sound of that, then subscribe here on YouTube, head on over to insulin360.com where you can join the newsletter and receive regular updates from me. And with that, let's get on with the episode. So why did I start the podcast? Well, throughout my studies, insulin kept on coming up, and more broadly speaking, metabolic health. And it was clear that this goes way beyond just our energy metabolism, the turning of food into ATP. Of course, this is important, but metabolic health has profound implications for every single system of the body. So if we want to be happy and healthy and have good mood and good energy and be effective in our day-to-day activities, then it's clear that focusing on metabolic health is important. And conversely, when these metabolic systems start to break down, that's when we start to see the emergence of symptoms and ill health, and potentially further down the line, chronic disease processes. So I decided to do my final thesis on insulin issues. I was looking at the various different effects on different tissues and how it's regulated, and going beyond blood sugar regulation to look at how it regulates other macromolecules and also other processes in the body that are connected to all sorts of different systems. And the thing which came out of this, which was interesting, was that it's much more useful to focus on the dysfunction of insulin rather than whether it's good or bad. There's this tendency these days to categorize things as good and bad because it's easier to think about things in that way instead of get into the details as to why they might be good or bad, or in what situations they might be good or bad. But what I found useful was really the context around insulin, and this applies to, of course, everything we see in health. Is it high or is it low is a kind of reductionist question to be asking. What we should be asking is it high when it should be high, and is it low when it should be low? Because in this case, if it's high when it should be high and low when it should be low, we're talking about good metabolic function. We're talking about the ability to adapt successfully to our environment, to the food that we're eating, to the various different signals that are coming in. The problem is when it's high and it should be low, or when it's low and it should be high. And this is what would be a maladaptive response. This is what would be dysfunctional. And that's where we start to see the symptoms and the poor health and the increased chronic disease risk. So when it's high, insulin has all sorts of beneficial effects for the body. It's a state that is broadly categorized by the storing of resources, so storing of glycogen, protein synthesis, fat synthesis, and so on. But it's also a state where insulin is modulating enzymes to increase energy expenditure as well, and also doing other things like neuron growth, like mitochondrial biogenesis and so on. So there are very many beneficial effects of insulin, also on the pentose phosphate pathway, for example. When insulin is low, when we're in that fasted state, there are another set of beneficial processes going on, and these are largely opposed to those previous processes, but there is some overlap. So we're talking more about the liberation of resources, the liberation of glycogen, of fat stores, and so on. And but there's also mitochondrial biogenesis going on here with the activation of AMPK, and of course autophagy, which is an incredibly important process for cellular cleaning, for recycling some of the damaged and worn out parts of our cells. And it's clearly been shown that this is something that we want to maximize if we want to maximize health and longevity. So we have these two different states. We have the fed state where insulin is high. We have the fasted state where insulin is low. And ideally, we want to be able to switch between them as depending on the context, depending on what we're eating, depending on our environmental stimuli. And it's when we lose the ability to switch effectively between those that we then start to see metabolic dysfunction. And so then the question was, well, why does it become dysfunctional? It's not insulin the root cause, it's what's going on further upstream. And it's what's happening in the broader network. So not looking at insulin in a reductionist way, but taking a more systems approach. So of course, the big factors in the scientific research are diet and exercise. But there are other factors as well, like for example, air pollution, circadian rhythms, other synthetic chemicals that we might find in our environment, poor sleep. Then we have psycho-emotional stuff like stress management, like adverse childhood events, like loneliness. All of these factors impact these metabolic systems. They impact a whole series of different hormones, and they can result in metabolic dysfunction when they are not optimized, when there is some issue with them. And so the aim of the podcast is to explore each of these areas with various different experts in their field, because there wasn't enough space or time or my expertise to go into these different areas in the thesis. And so that's really the scope, to go and speak to knowledgeable experts in various different fields and to translate that into information that can then be put out in a sort of digestible form as part of a podcast that people can then make use of in their day-to-day lives. And the reason why I think this is such an important area for us to be looking into generally is that we've seen an epidemic of chronic disease in the last few decades, which is only increasing and accelerating. And this is a kind of silent epidemic that we don't pay enough attention to, but it has such a broadly negative effect on so many different areas of our society. The thing is that it's just so slow moving that it never really gets enough attention. But it's estimated that in the year 2030, we'll be spending around about $47 trillion globally on dealing with chronic disease. There's people who can no longer work, can no longer live happily, can no longer be a functioning part of society. And this number is growing and growing and growing, and people are getting younger and younger and younger that are affected by this. And so, of course, longevity, the fact that we're living longer, and genetics plays a role. But these problems are primarily down to the way that we live, what we're eating, circadian rhythms, exercise, stress, all of the things that I mentioned before. And so it may sound a bit dramatic when we say that, okay, at some point this increase in chronic disease is going to become unsustainable. At some point, our societies will no longer be able to support themselves as that percentage of sick people increases in our society. But of course, that's compounded by the fact that our societies are getting older and older. This is happening both in Eastern societies like Japan and China, and also Western societies as well. But the positive side of that is that because many of these factors are environmental, it means that we do have the opportunity to make changes. And so we can change the way we eat. We can change our circadian rhythms, our exercise schedules, and so on, at whatever age and in whatever situation, to improve our metabolic health and to reduce this risk of chronic diseases. And so it's not just about the economic impact. It's also about the personal impact, because dealing with chronic disease and symptoms it is difficult on a personal level. It's difficult for the person if they can no longer work or support their family or be a functioning part of society around them. And so it's difficult for families and the society at large. So that's the aim of the podcast, to delve into some of these areas, to explore some of them, and to put that out into a format that people can then make use of to improve their own metabolic health, to improve their own lives. So with that said, let's get on to some of the history. So let's now take a brief look at the history of insulin. I think it's a really useful exercise because firstly, we can see just how far we've come. We perhaps take for granted that we can go on to PubMed or Google and we can find hundreds of thousands, if not millions, of scientific articles explaining all of these different factors in great detail. But it hasn't always been like that. And certainly in the last 100 years since the discovery of insulin, we have seen an exponential growth in our knowledge and understanding around these areas. And it's really interesting to think back to those early researchers and to contemplate that the vast majority of knowledge that we have available today, they didn't have access to. And so in that way, it's interesting to watch this progression, to see how collectively knowledge was being expanded, inching forwards. And then we have these breakthrough discoveries where kind of the whole landscape changes. And so I think it's good. Yes, it gives us an appreciation for where we've come from and perhaps also a sense of where we're headed as well in 5, 10, 20, 50 years down the line. There's likely to be some incredibly exciting developments looking at all of this. And not only, but the second reason why I think it's a nice idea to look at the history is to go back much further in time to a time when they didn't have the scientific perspective that we have today. So looking at the traditional Chinese medicine or Ayurveda thousands of years ago, where there was no knowledge of the existence of insulin as a molecule, but they still had to deal with the same sorts of problems, albeit on a lower scale, surely. And so they developed different ways of managing these problems, different ways of observing these problems and treating them. And so it's useful to go back and look at this because they can give us interesting insights in the ways that we are looking at these problems together. So let's take a look at the history then. This starts way back in 1550 BC with the first written record of something like diabetes. And this was in Egyptian manuscripts. And I think they were describing like the symptoms that were observed. And they would use, I think, a whole grains diet to try to treat insulin issues back in those days. And so increasing dietary fiber to try to decrease the glucose burden, I'd imagine. We then move forward to around about 800 to 600 BC, up to around about 200 AD. In this broad period, there were two important figures, and these were two Ayurvedic doctors. One was Sushruta and one was Charaka. And these guys are interesting because they are credited with many of the founding principles of Ayurveda, but they're also credited with many things to do with modern medicine. For example, Sushruta was the first plastic surgeon, supposedly. He was doing nose adjustments thousands of years ago using alcohol as anesthetic. And they had a very advanced knowledge of medicine for those times. And in actual fact, it was Sushruta who was saying 600 BC that a sedentary lifestyle was a key component of why people went on to develop these conditions. Now, he wasn't referring to type 1 sort of conditions, he was referring more to the type 2. And around this time, there seemed to be the first distinction between these two different conditions. So the type 1 being the early onset with the weight loss and the other symptoms that go with it, leading to early death. And the type 2 being more related with obesity, with a sedentary lifestyle, and with it appearing later on in life. And so it's amazing to think that he picked out exercise as being key to dealing with diabetes and obesity more than 2,500 years ago. So that was, yes, around that time there was also the first diagnostic test that was used. And this is where they used ants to see whether the urine was sweet or not. So if the ants were attracted to the urine, then the person would get the diagnosis of matumea, which I think translates roughly to honey urine. It's interesting because later on there are records of doctors doing the same thing, of doctors tasting the urine to see if it was sweet or not. I think I prefer the ants version of this test. So, where did the term diabetes come from? Well, later on, around the late 3rd century BC, this is attributed to Demetrius of Apamea, and he presumably coined this phrase because it means to go through or to siphon in Greek. And this was noted because of this increased thirst and this increased urination that was observed in these people. Later on, these conditions were talked a lot also about Aristeas the Cappadocian, and there's some confusion as to maybe whether he came up with this term, but perhaps he was citing this earlier term. And regardless, he wrote extensively about these various different conditions. One quote which I found particularly interesting was this one, where he said, "No essential part of the drink is absorbed by the body, while great masses of the flesh are liquefied into the urine." Now, this is kind of graphic, kind of suggestive, but it very accurately describes the nature of diabetic conditions, because there's not only the increased thirst and the increased urination as people try to flush out that extra glucose from their system, from their blood, but there's also this catabolic nature of these conditions. So as blood glucose is not getting into the cells, then there is increased catabolism of protein and of fat, and this causes the weight loss that is seen in type 1. And so, yes, already by this stage, there was some very accurate descriptions of what was actually going on, even though there was at this point no idea that the molecule insulin was having a role to play. So fast forward a good few years, we're in 1889, and there was a famous experiment by Oskar Minkowski and Joseph von Mehring. And with a dog that had the pancreas removed, they were able to observe the development of diabetes. So this was the first time that the pancreas was causally involved in the progression of this condition. Then later on in 1910, Sir Edward Albert Sharpie Schaefer, that's an incredible name, he put this down to a hormone imbalance. So he was saying that maybe the pancreas produces a hormone called insulin, and it was called that because of the islet cells where he presumed that it was produced. Maybe it's this imbalance that is causing this condition. So then later on in 1921, there was more research around these islet cells, and Frederick Banting came up with a novel approach to isolate these cells. And he approached John MacLeod, who was a professor of physiology at the University of Toronto, who gave him a lab space and a research assistant. And they were able shortly after to reverse diabetes in dogs using an extract from healthy animals of these islet cells. And only shortly after, in 1922, was the first time that this was used in a human subject. So this was 14-year-old Leonard Thompson, and he was injected with this extract, and he was able to live another 13 more years, which was an incredible leap forwards because type 1 diabetes had no known treatment in those times. So in that same year, glucagon was discovered, glucagon being the kind of mirror image of insulin in many ways. And the researchers, Campbell and Merlin, they named it glucagon because it's an amalgamation of the two words glucose agonist. And this was later purified by two more researchers, Sutherland and Duvet. And so this then gives rise to another branch of research around glucagon. So in 1923, Banting, Best and MacLeod, they got the Nobel Prize for their work. And later on in 1936, another fantastic name, so Harold Percival Himsworth, he was the first person to suggest that type 2 could be to a relative deficiency rather than an absolute deficiency. So at that point, it was understood that in type 1, there wasn't enough of this insulin flowing around the system to do its job. But he suggested that maybe in type 2, there was enough insulin, there was plenty of insulin, it just wasn't able to act on the cells because of some sort of resistance. And this is exactly what's going on, we now know for sure. So while this clinical side was moving forward, there was also the molecular side moving forward. And so in 1935, we have the first diffraction images of insulin crystals from Dorothy Griffith Hodgkins. And later on, she went to, she received the Nobel Prize for Chemistry for this in 1964. And a couple of years later solved this puzzle and suggested that insulin was composed of 3 heterodimers. So this was a description of the structure of insulin. Similarly, a few years earlier in 1958, Frederick Sanger got the Nobel Prize in Chemistry for his work on the amino acid sequences of the A and B chains of insulin. So at this point, there was a lot of work to improve the quality of these extracts of these islet cells from animals in order to be able to be used as medicines in people. And so through the 50s and the 60s and 70s, there was improving extracts, and this was firstly the U500, and then it became more commonly U100, and this was an extract that was used to these ends. And so as the treatments were improving and life expectancy was increasing, there was a kind of shift towards, well, people aren't dying so young. What's happening if people are dealing with long-term higher blood glucose levels? What are the long-term implications? And so the research shifted slightly towards that. So it's worth mentioning 1960, a famous study, the UDGP study, and it was one of the first American randomized controlled trials. And it was looking at fenformin, which was a predecessor to metformin. And although it didn't show any mortality benefit, it was a kind of landmark study because many of the techniques of the scientific method that we are used to today, like using randomized controlled trials to try to find out any differences, were kind of in their infancy in this time. Later on, 1968, we've got the discovery of HbA1c by Professor Samuel Rabar. This, of course, is interesting because it's still used today. It's still one of the mainstays of diabetic care because it gives an average blood sugar level over about the lifespan of a red blood cell, about 3 months. And so it's measuring the glycosylation of these cells. Then in the 1970s, we also have technological improvements as the first blood glucose machines started to become available. And in 1999, there was the first continuous glucose machine. And I mention this because it seems like it should be much more recent than this, but actually they were starting way back in the 90s for the continuous one and the 70s for the standard machines. And I guess at this stage they were kind of prototypes and perhaps a bit crude, but it represents an important advancement because then people could start to measure their blood glucose at home in response to medications and lifestyle changes and other things going on for them. And so this really improved the standard of care for these patients. And of course, today it's completely normal that people regularly test their blood for their blood glucose levels, and also have the continuous meters, which now are kind of the size of a coin and a sensor which goes into the back of your arm. And so the technology has really moved on. In 1978, there was the first insulin that was created in the lab from E. coli. That was the work of David Gödel. And this led to 2 drugs, Humulin R and Humulin N, in 1982. And this again represents a leap forwards as preparations become more standardized, production could be scaled up, and this could be used to help a larger number of people in their treatment of type 1. And I think around this time they were also starting to use treatments for type 2 as well. We'd seen some of the early studies on diabetic drugs. And many of these were developed, for example, from plant compounds, observing what herbs had been used for thousands of years, for example, in Ayurveda and in traditional Chinese medicine, and extracting compounds from those plants. For example, also from Western herbalism, I think metformin comes from the French lilac, for example. So as that's moving forwards, there's a shift always towards the effects of blood glucose and the long-term complications. But it was only in the 90s that glucose was causally linked to these complications. Of course, it had been suspected for years, but in 1993 there was the Diabetes Control and Complications Trial, and in 1998 in the UK, the UK prospective diabetes study. And these were the studies that cemented blood glucose as the bad actor for the negative effects of diabetes. So the high blood sugar levels leading to kidney issues, to eye issues, to atherosclerosis, to glycation end products, and increased oxidative stress. This was the beginning of all of that. And of course, we now know that also insulin plays a role, higher levels of insulin play a role in this. But it wasn't until lifespan was being increased that then they were turning their attention more to these longer term complications and how do we live with this condition. There were then more drugs that were coming out, more versions of insulin like Lispro and Aspart, and then later on in 2005 Detamir, which was a longer lasting formulation. And so all the while this was improving people's treatment possibilities. Moving further forward, then there was always more interest in what was happening inside the cell. And so there was some seminal research by Gerald Schulman, ongoing research which was first published in 2000, that was looking at the idea of, well, where in this insulin cascade are things beginning to break down? And so he was using a novel imaging technique which was allowing him to analyze this and look closely into the cell, not only in in vitro studies, but actually in humans. And so this research led to the discovery that diacylglycerol, or DAG, this fatty substance, was building up in the cells and inhibiting that insulin signaling cascade. And okay, so the research has moved on, looking at ceramides and other compounds, but this remains an important moment, I think, because it's then that we're looking at perhaps why. Why is there a buildup of this DAG in the cells? And so perhaps that was the start of looking also at maybe it's to do with mitochondrial dysfunction, maybe it's to do with oxidative stress or inflammation, maybe it's to do with overnutrition. And so all of these areas were then becoming more heavily researched in this period. So moving forward, there was in 2009 a trial worth mentioning, the ADVANCE trial, and a year later also the ACCORD trial, a similar trial. And they were looking at what happens when you aggressively treat blood sugar and you try to reduce that HbA1c. They found some benefits, but it wasn't like finding a cure. And so that kind of opened up the question, well, if we lower blood sugar, where is that blood sugar going? If it's just being turned into fat inside, for example, liver cells, then that might be creating more metabolic dysfunction further down the line, even if we're reducing some of the effects of the high blood glucose. And so I think we see this shift towards asking why, always asking why something is coming about, and what are the drivers of this. And we see more research into diet and into exercise and circadian rhythms and cortisol dysregulation, all of these other things which have come on since. And so, yes, I think it's worth, I won't go into detail into lots of other studies because we would be here forever. And also that's the kind of, those are the kind of things that I want to speak about with many of my guests which come on the show. And so the research that has happened in the last 20, 30 years, what new insights do we have around the mitochondria and around cellular phenomenon that may be leading to all of this. So that's about it for the history of the recent history. I think it's worth finishing with an example from further back in time, just as an example to show us about different perspectives. So if we go back to traditional Chinese medicine thousands of years ago, in ancient China they didn't have the benefit of biochemistry or a molecular viewpoint of what insulin actually was. So they had to develop different ways of dealing with these problems. And so they based their approach on observing nature, on observing the cycles in nature, the seasonal cycles, the day-night cycles, and applying that to human health and to human disease. Because it was their assumption, they believed that everything in the universe was governed by the same principles, by the same natural laws. So just as an example, if they saw in springtime sprouts growing, springing up, bursting into life, this is very much for them a wood energy. So they see this as a transformation. The philosophy of traditional Chinese medicine is built on energetic principles because it's dealing with the transformation of things. And so this springing up of the sprouts in spring is definitely a wood element as the energy goes up and out. And so they apply that same concept to humans, the capacity to go up and out, the capacity to synthesize, and also on a psycho-emotional level, the capacity to have determination. If we think about the tiny sprout in spring, the determination that it has to live and to grow and to succeed in this huge world, even though it's very delicate, this is perhaps a concept that we can apply to also human behavior. And so we hear a lot about yin and yang, and this may seem a little bit nebulous for people, but in traditional Chinese medicine, insulin issues would usually be classed as a yin deficiency. There are other classifications to do with the qi and the spleen, but what does that actually mean? So they, like I say, they see the world in these energetic transformations, and yin and yang are these two opposing yet interdependent energies which are in constant transformation. And so, for example, they would describe a yang energy as midday, as summer, as pure energy, as perhaps more the masculine energy, whereas they would describe yin as more midnight, as the moon, as more able to create structure, winter, perhaps the more feminine energy. And so as we see the cycle from the summer, which is a moment of full yang, around to autumn, it's transforming into yin, and then round into winter as it becomes full yin, and then back round into spring and summer, we can see the kind of transformation they were alluding to. And so to give that perhaps a real life example, why would they see insulin issues as a yin deficiency? Well, what does insulin do? It's an anabolic hormone. It creates structure. It stimulates protein synthesis and glycogen synthesis and fat storage and so on. And so this is also, when we look at natural cycles, this is also something that happens from the summer through the autumn to the winter. Animals stimulate these processes so they can turn energy into stored energy so that then they can have a better chance of surviving the winter. And so for in traditional Chinese medicine, this yin deficiency means the inability to actually do that, some of those processes being blocked. And so that's why I say they didn't have a concept of insulin as a molecule, but they had the concept of what it did in the body, this storing of energy in preparation for the winter, for example. And so it's also interesting to think about our lifestyles as well, because traditional Chinese doctors look very much into the lifestyles of people and how people are living. And if there is a yin deficiency, then there could be caused by an excess of yang. And if we look at our culture at the moment, it's very much a yang dominant culture. So we're working all the time. We're searching for stimulation, either in the things we eat or drink, or the things we do, technology. We often stay up late, stimulated by artificial lights and motivated by our careers and so on. This is very much a yang dominant moment in history. And so for traditional Chinese doctors, this would be no surprise that we then start to see these epidemic of diseases that they would class as yin deficiencies. And so yes, they speak perhaps in metaphorical terms. It's difficult for perhaps people from a Western point of view to fully understand their point of view. But hopefully that gives you an idea of how different perspectives can give us insight into some of these the same kind of situations that they're both trying to deal with. So then, that's about it for the history. Now we're going to move on to some of the basic physiology around insulin. So let's now take a quick look at some of the basic physiology around insulin. So where is it produced, how it moves around the body, and what different effects it has on different tissues. So insulin starts out life as pre-proinsulin, which is a peptide product of the INS gene in the beta cells of the pancreas, and we can find those in the islets of Langerhans. And previously, talking about the history, these were the areas of the pancreas that they were trying to purify to make these extracts that were used in treatments. And so this pre-proinsulin then moves out of the ribosomes and is transformed to proinsulin and then insulin. And this insulin is stored in granules inside the beta cells. And when there is a signal for it to be released, these granules move to the surface of the cell, fuse, and then allow the insulin to go out into the bloodstream. So what are these signals? Well, mostly we're thinking of glucose and amino acids. And so we know that when we eat carbohydrates and to a lesser extent protein, they stimulate this insulin response. But there are other things as well. For example, certain plant compounds, there's ethanol, some glycolytic intermediates, and also some hormones are able to amplify this effect, like GLP-1. So the plant compounds are interesting because often we find these in herbs that have been used for thousands of years in Ayurveda or in traditional Chinese medicine. And so now that becomes the focus for research. How do we isolate these molecules and use them? The plant effect is a lot weaker than, for example, certain drugs. But plants often have a more systemic effect. So, for example, the Ayurvedic herb Gymnema sylvestre, this has been shown in research to have this effect of stimulating insulin response. But it also works on the way that we sense carbohydrates in our mouth, and also that we absorb carbohydrates or glucose in the gut. And so it works on many different levels, even though it's not as strong, perhaps, as our modern pharmaceuticals at stimulating this insulin response. Ethanol is another interesting one because many people report that when they drink, they notice lower blood glucose levels. And that's because ethanol stimulates this same response. This is, of course, something that diabetics have to pay attention to, because if they're already taking insulin and then they have a few drinks and stimulate more insulin release, then they're perhaps risking hypoglycemic events or diabetic crashes or maybe even comas. And it's also interesting to think about how this works in other mammals as well. Xylitol, for example, is a wood alcohol that is used as a sugar substitute. And we're finding this more and more in chocolate and in chewing gum and things like that. For us, it doesn't really elicit any sort of insulin response. But for example, in dogs, it can stimulate a very strong insulin response. And it's really quite potent as well. I was calculating that our smallest dog, she weighs about 7 kilos. She would need perhaps more or less a gram of xylitol for it to be a fatal dose. And of course, in that situation, it's something we should be aware of, because we need to get our dogs to a vet quickly to get a glucose infusion to counteract that drop in blood glucose if they come across something with xylitol in it. It's also interesting to think about how in nature some of these systems get used for other purposes. And for example, there's a certain type of cone snail that uses insulin as a weapon. And so it's evolved to be able to inject insulin into its prey, into this certain type of fish. So insulin is then moving around the body after being released from the pancreas. What happens then? Well, it has to have its effect on cells, and so it binds to these receptors on the outside of cells, these tyrosine kinase receptors. And these are what's called transmembrane receptors. So they've got a little bit poking out of the cell, the alpha subunit, and a little bit poking into the cell, the beta subunit. And so insulin binds to the alpha subunit, and that causes changes that then affect the beta subunit. And this triggers an autophosphorylation reaction, which then stimulates a whole cascade of different reactions throughout the cell. So in proteins, one after another, they get activated or phosphorylated, which then results in the end effects of insulin. And so perhaps the most well-known effect of insulin is the effect on blood glucose. And so it stimulates these, at the end of this chain, these GLUT4 proteins to move to the cell surface. They're contained in vesicles. They then are released and fuse, and then allow glucose to passively diffuse into the cell. So the blood glucose goes down and the cellular glucose goes up. That's the most well-known, perhaps, action, but it's one of many, because along that protein chain there are also other things happening. And so a key protein, for example, is AKT, and that seems to be a branching point for lots of different functions, because it also leads to the stimulation of mTOR. And so mTOR is going to stimulate protein synthesis. There's also going to be cell growth. There's a mitogenic effect, and also in stimulating glycogen synthesis through GSK3 beta signaling and neuron growth as well. And there are also effects on cell survival because of the modulation of the FOXO genes. And the AKT pathway is worth mentioning because it's being heavily researched for cancer research. In cancer cells, this pathway seems to get distorted, and the cancer takes control of this pathway to stimulate more growth. So that's basically how insulin works. It binds, it creates changes inside the cell, and that leads to changes in proteins, which lead to the final effects of insulin. So let's go through a list of some of those effects on various different tissues. Because there's not only effects on the physical body, there are also effects on our psycho-emotional state, on behavior and on learning and so on. So first of all, we've got this glucose uptake by increasing GLUT4 translocation. We've then also got this increased synthesis of glycogen, and also the reduced breakdown. So glycogen are these long chains of glucose that we store in our muscles and our liver and in other tissues for quick energy release. It increases the synthesis of fat. And this is an interesting one, because in general this is seen as a negative thing, because we all want to remain lean. But this is, of course, an evolutionary adaptation. The fact that we can put on fat and then tap into that fat in times of scarcity is the reason why we're still here. It's a survival mechanism. And insulin plays a key role in that, also because it modulates enzymes like lipoprotein lipase. And it seems to increase the activity of that at the fat cells and decrease the activity of that at the muscle cells. And so when we've eaten, we've likely got resources available for the muscle, glucose and so on. And we're trying to direct any extra resources over to the fat cells so we can store them for future scarcity. And so what lipoprotein lipase does is it breaks down triglycerides and VLDLs and so on into free fatty acids and glycerol, so that can be taken up by the cells. And then insulin also stimulates the process of esterification. So inside the fat cell, there's then the process of putting these free fatty acids and glycerol back together so that they can be stored as triglycerides and so on. And so what I want to try to get across here is there is a kind of intelligent partitioning of energy. Insulin is like a metabolic switch, where it's deciding where resources should go, and it's deciding how they should be stored or used to make the best of either the fact that we have got food available to us or we don't, and we need to tap into those resources. So then we could also say that it reduces lipolysis and the breakdown of protein, and also suppresses gluconeogenesis in the liver and the kidneys. This is an important process. Gluconeogenesis is the process by which we generate glucose endogenously from things like lactate or glycerol. It mostly happens in the liver, but also in the kidneys. And insulin has the effect of putting the brakes on this process. And so if we've eaten, our blood glucose level is rising. We no longer have the need to generate endogenous glucose, and so insulin slows that process down. But what happens, of course, is if we get resistant to insulin at the level of the liver, then this process doesn't get slowed down, and this can start to raise up. And this is one of the key drivers of increased blood glucose, the key contributors to it. And so this again, we're seeing the difference between the fasted state and the fed state and the intelligent use of resources. And so if we can adapt to that, if we can adapt to the resources that we have available, then insulin is incredibly beneficial in the things that it does. It also increases amino acid uptake, DNA replication and protein synthesis as we've seen. And so it works on lots of different levels of the chain. The same thing with glucose. It's not just about increased glucose uptake or increased glucose availability. It's also about modulating some of the enzymes along the glycolytic pathways to increase the production of energy, or also doing the same with the mitochondria. So it may actually be important for mitochondrial biogenesis, like we've mentioned previously, and also the health of the electron transport chain. And so good insulin functioning is important for good mitochondria, and at the same time, good mitochondria is important for good insulin functioning. So this is kind of bidirectional relationship. So there are also changes in arterial blood flow. This is an important thing to touch on, because often we think of insulin as being involved in blood sugar, but it's also important for blood pressure. And there are several mechanisms by which, when insulin starts to become dysregulated, our blood pressure can start to rise. One of those is that insulin increases sodium and water retention at the level of the kidneys. Another is that it increases the production of renin, which is the first stage of the RAS system, which ends in the production of angiotensin II, which is a potent vasoconstrictor. And of course, that would raise our blood pressure. And the last one worthy of mention is that insulin has this interesting relationship with nitric oxide. Nitric oxide has also been shown to be an insulin sensitizer, but with insulin dysfunction, there is less production of nitric oxide at the level of the endothelium and more production of this chemical endothelin-1, which some describe as a pro-inflammatory cytokine. So why is that a problem? It's a problem because nitric oxide is a vasodilator and very important for healthy circulation, and endothelin-1 is a vasoconstrictor and will raise our blood pressure, and also potentially initiate oxidative stress in the endothelium and chronic inflammation and so on. So again, we want insulin at the right level at the right time. Too much is going to lead to the increase in blood pressure, maybe endothelial inflammation and oxidative stress, but we also don't want too little, and so it's about the appropriate response. We can also touch on some of the psycho-emotional aspects of insulin. Insulin, there's some new research looking at how it may interfere or regulate the endocannabinoid system. This is difficult to apply clinically, and so as this is a new area of research, it's something to watch. But something that's perhaps better well known is the effect on our feeding behaviors. So insulin interacts with the hypothalamus together with other hormones like leptin and ghrelin to modulate our feeding behaviors. And it may also modulate social interaction as well. So often we'll be eating together, socializing together. This may be something that insulin is able to encourage. So another important thing is that it seems to help with memory consolidation as well. There's something to do with cognitive function with insulin. And this is a kind of interesting parallel, I guess, because when we look at it in the physical body, it's about storage and consolidation of resources. But also on the brain, it may have this psycho-emotional capacity, or this psychological capacity, I should say, to actually store memories and consolidate learning. So there may also be important effects of insulin on neurotransmitters, and so it probably has an important impact on mental health in general. And in fact, with people with diabetes, there is quite a significantly higher risk of both anxiety and depression, and this may be down to some of these factors. One is that it seems to be able to modulate dopamine signaling in the brain, and also potentially to reduce serotonin levels in the brain as well. And this may be for a number of reasons. One thing which researchers look into is the activation of the kynurenine pathway. When insulin signaling is dysfunctional, there is a lower level of NAD+ to NADH, and so one of the objectives of the kynurenine pathway is to reset that balance, but that can have some negative effects on brain health with substances which have been linked with anxiety and neuroinflammation and so on. Insulin also seems to protect against neurodegeneration. It seems to regulate GABA receptors, NMDA receptors, and so on. And also seems to regulate astrocytes as well. These are all of the sorts of things that I'm hoping to talk to researchers more about, because during the thesis I was making a list of these things and reading some research, but it's not completely clear because these are complicated areas. And so as we go forwards, it's going to be interesting to see how we can develop this area, looking at insulin as an important factor in mental health. So that's about it for looking at the basic physiology around insulin. Hopefully that will give us a good idea of some of the functions moving forward, so that when we're talking to our guests, we can better digest what they have to say. So that's about all we've got time for today. I hope you found that useful and interesting. And if you like what you heard, by all means subscribe to the YouTube channel and head on over to the website to sign up to the newsletter to receive regular updates. Have a great day and see you soon.